Yeah, so right now is towards the end of week 13 already, right? So we have what, 2 more weeks, and then after that it's going to be the exam period. So towards the end of the semester already. So around these days you should be today is the day for you to do the quiz, submit tomorrow, and then don't forget the assignment. So 2 weeks left for the assignment. Yeah, so we'll choose the topic and work on it, and yeah, just let me know if you have any question, right? So it's just 2 things for us for this course, and then for the final exam. Okay, so yeah, so that's about it for today. Free week for review, wait, let me see. I think I don't remember. Depends on the exam schedule. So I'm not sure. Yeah, I need to check the exam timetable. I can let you know later. I don't know if we have free week for review, but I believe, right, at least for our course, we should finish before, maybe hopefully I will finish all the topics on the Monday of week 15. And then Wednesday, I will review, then after that, everything is free. Wednesday, I will just like review and recap the things that we have learned so far. Okay, yeah, so that's about it. Any other question before we continue? So if not, then we continue on for the Doppler effect. Yeah, so 18th January, which means that there's no free week for review, unfortunately. Yeah, yeah, so our final week is January 15, right? Yeah, unfortunately no. And partly the reason is, I guess we can know why because our semester actually start late this year because of the virus, right? So because of the pandemic, we everything pushed back by a few weeks, so there's not enough time for review after that because the next semester have to start already. Okay, so yeah, so unfortunately we can blame the virus because of this, blame the pandemic. Okay, so we continue on to talk about the Doppler effect. I already started last week already, right? So let us discuss this properly. As I said just now, right, we have plenty of time, so we can do this slowly and make sure everyone understands everything perfectly, right? So what we're going to do is to talk about the Doppler effect, where the waves that we are discussing are now sound waves, right? So sound waves is they also propagate like a sinusoidal wave. They have a wavelength and they have a frequency. So if I draw the graph at time 0, it's going to look like that based on the different locations, right? So the vertical axis here is about the pressure. So this is about how the pressure changes, and this is how we detect the sound waves, and the frequency of the sound that we hear is the frequency of this vibration of the wave. So notice that this will be important for Doppler effect is because, right, if we are moving relative to the sound, the sound that we hear actually changes frequency, and the reason is because, right, imagine all this sound wave going into our ear. So the time interval between the maximum one cycle, right, between the first and the next maximum depends on how fast the wave is going into your ear, right? So, and your ear will measure this, and that is what you hear as the pitch and the frequency. So that is the general idea to help us understand the Doppler effect, is that, you know, if we have a sound coming in, right, and then we are running towards the sound, so the time interval of the pressure maximums coming into your ear, all the cycles go into your ear faster, and then your ear will detect this as your changing of the frequency, higher frequency. If you are running into the sound, right, you will hear more cycles per second, then you'll hear a higher frequency. If you are going away from the sound, right, so the cycles per second coming into your ear is a bit slower, the sound trying to catch up with you, so the frequency in this case will be lower. So that is the intuition that help us understand why the Doppler effect happens. So now we can, using this basic idea, we can try to do some calculation because of this. So how can we get the frequency? Is because it depends on the speed of sound. So frequency is related to wavelength by f lambda, right? So if we running into the sound at a certain speed, then we will detect a certain frequency. So if this is the velocity relative to u of the sound, and then this is the frequency that you hear. Okay, so let us start our first case, which I already calculated on Monday a bit quickly, but now I will do it properly now. So now we discuss the case about the moving observer and stationary source. Okay, so what happens with a moving observer and a source that is stationary? So let's say, right, the observer is running, right? So it's moving. So it's moving at some speed, v0. Okay, it's moving towards the sound. And then the source is not moving. Okay, so this is my source, and this is my observer. So the source is not moving, so 0 speed, but the source is emitting the sound waves. So let's say is making some sound, so it got some loudspeaker, and then the wavelength is lambda. Okay, so what we have here is that our source emits sound at frequency fs. Okay, so f source, right? Then this is the sound emitted by the source, right? So a sound also is emitted by vibrations per second. So if you have vibrations per second, then it will cause the wave to come out through the air, and this is how you get the wavelength and the frequency and the speed of the wave, right? So because it's vibrating, is some speaker vibrating at some frequencies per second, then the wavelength generated can be calculated. Is based on what? Well, the speed of sound, right? So v is the speed of sound in air, is given by this. So the wavelength generated will be v is equals to the frequency of the source times lambda, which in other words, lambda is equals to the speed of sound divided by fs, right? So this is the wavelength generated, and then this wavelength is having the wavelength lambda, right? Whatever, how many number of meters, and then it's going at this speed. From there we can determine the frequency. It's passing through the air right now. Okay, so now we see what happens if the observer listens to this sound as the observer is going in this direction. So so let's write this as observer measures what? So first of all, what is the wavelength? Well, the wavelength is just lambda. So wavelength is what the observer sees will be just lambda, so it's just v over fs, right? So it's the same thing. And then the speed of the wave is what? So the speed of the wave, right, is measured by the observer. So it is actually v plus v0 is relative velocity, right? So if the speed of sound is 340 meters per second, and then you're running towards it at 10 meters per second, you get 350, right? So you add up. This is the relative velocity. So this is relative to the observer. Okay, so in other words, based on this information, what is the frequency observed? Right, so we use the relation speed of sound, right, is equals to wavelength times the frequency. Okay, so the speed of sound is, this one is for the observer, you know, this is relative to the observer. So the observer speed of sound is going to be v plus v0, and then the wavelength, well, the observer will just look at the wavelength and see that is how many meters of lambda, right? And then the frequency is the frequency that is what we want to calculate, the observed frequency. And the wavelength expression we already gotten, so we put this inside here, right? So we find that v is equals to v over fs, and then the frequency observed. So the observed frequency is just bring this over, so I got v plus v0 over v times the frequency of the sound. So it's not equals to the emitted sound, but is changed by this factor. Okay, so so this will be a larger number, this will be a smaller number. So if you run towards the the sound, you will hear higher frequency, right? So this is the result that we get upon running towards the source, right? This is the frequency that you hear. Any question? Yes, yeah. So that. So yeah, this one I will discuss about this because EM wave is a bit strange. EM wave has a Doppler effect, but it's a relativistic Doppler effect. So it's a redshift, and it depends on relativity, which we'll actually learn later today, right? Yeah. So correct. So this one is something we'll discuss, something that we will discuss later about relativity. Speed of light is always constant. So speed of light is always constant, but now we're talking about sound. So sound is, we have got relative velocity. EM is two wave combined into one. Yes, also yes. So the details also we will learn in the next course, right? So there's a lot of complicated ideas tied together when we talk about light as an electromagnetic wave, because electromagnetic wave, the EM wave is a wave in the electric field, and then there's another magnetic field in this direction. So it's these two waves that is propagating, and then this, when we come into our eyes, we see as light. Yeah, so that is true, correct. And then the speed of light, right, is a bit strange and different because the electromagnetism obeys special relativity. So we need to understand special relativity as well. So this calculation does not apply to electromagnetic waves. Yeah, so we'll actually learn this when you learn more about electromagnetic waves. What we will learn today is relativity. So that's gonna be interesting and weird because relativity is where you get all the interesting and weird concepts. By the way, right, I have an announcement to make. I should say before I forget that our physics department, one of our colleagues is looking for student helpers. If anyone is staying on campus, if you want to help out, the help is very easy. It's just that there is a competition for high school, and then we are printing out certificates, right? So there's a lot of certificates. So we need a student to help to I think to just chop the certificate. The printing is done, I think, already done. So if anyone wants to help, right, let me know. I will give you the contact of the lecturer who is arranging this. Okay. Yeah. Price. I'm asking him the price as well. Waiting him for a reply. Will you be willing to do for free? Will you be willing to do work for free? So I'm asking him, waiting for reply lah. Is there any payment or not? Yeah. You're not on campus, huh? Oh, okay. Yeah. So Johi, you can. Okay. So I think more than one. If more people help out, then it might be better lah. Yeah. So okay. So if we talk about the later chapter, don't worry about it lah. It's just like it's just like random talking only, because it's really the stuff that we learn in the later course. But relativity today, chapter 8 is oscillations. Where we are finishing up chapter 9 right now, and soon we will start on relativity. Yeah. Okay. So now, so let us continue with the other case. This case, right, is actually observer going towards the source. So if the observer is going away from the source, what happens? So let us calculate this. So observer okay, so what is the solution, right? So let us do this calculation here, right? So if my observer is now running away from the source, right? So my source is here, okay. Okay, and then the wavelength is still lambda. Then what does the observer measure? Okay, so the wavelength is still the same because wavelength is wavelength, right? For sound, we have no relativity, so wavelength is still lambda. So lambda is still v over frequency of the sound. But what is the speed of the wave? Okay, so the speed of the wave now is moving away, right? So the wave is traveling at speed v, and then the observer is moving away. So the speed of the wave relative to this is v minus v observer, right? So relative to observer. Okay, and then so from here, what is the frequency observed? So frequency observed is using the formula speed of sound is equals to wavelength times frequency, right? So the speed of the sound is v minus v0, the wavelength is v over fs, right? And then the frequency is what we want to calculate. So my f0 is v minus v0 over v times the source frequency. So I have a minus instead of a plus, right? So this is these are the two cases, right? So we have the observer going towards stationary source, and this is the observer away from stationary source. Okay, so yeah, the difference is just the sign. So you just need to remember it's plus for going towards, minus for going away, right? So it's pretty straightforward. But just in case anyone is still confused, I will show. I'm just showing more details. Okay. So yeah, so for the observer moving away from the source and towards a stationary source, the frequency changes, right? And the reason is because it's expected. Is because when we hear something, is the cycles per second. So if we run towards the sound, right, the cycles per second come into your ear faster. If you're going away from the source, the cycles per second is slower to reach your ears, and that is the reason. Okay, yeah. So observer is getting, I guess it's the ugly way I'm drawing this, is it? Is quiz 3 very difficult? It's not supposed to be, right? A few question is straightforward. I think I also don't remember what's in the quiz. I think one question is like some indirect thinking, but the others is like just plug in formula and direct calculation only. Should be pretty straightforward. Okay, so the next thing to do, right, is stationary observer, and is now the source is moving. Okay, so yeah, so now let's consider first source moving away. Okay, so source moving away, so I got the observer here, right, and then the source is going away, but the source is generating the wavelength, right? So we're gonna still call this lambda, and the speed of sound in the air is the v. But let's see what is happening here. If the source is moving, and this is the observer, so what's happening here, right, is that the source emits sound at frequency fs, obviously, but the source is going away at the speed of the source. So the speed of wave or speed of sound relative to the source, right, is v plus vs. Okay, so it is plus. So let's talk about speed, right? So the source is emitting sound going away from him at 340 meters per second. Then if I run forward some more at another 10 meters per second, so I will see the sound going away from me at 350. Agree, right? So plus Vs, right? So we got a plus. So therefore the wavelength generated, the formula for wavelength generated is going to be, well, using the formula V plus Vs, the speed is equals to f lambda, so frequency source times lambda, so lambda is equals to V plus Vs over Fs, right? So it's the formula we are still using is the speed, and then the frequency, and then the wavelength, right? So because of this frequency, and from the, this is from the perspective of the source, right? So the perspective of the sound source. So how about the observer detection? So let's calculate the speed of wave relative to the observer. Okay, so the speed of wave relative to the observer is just, well, the observer is not moving anywhere, so it's just the speed of sound coming in, right? So it's just the speed of sound, and then the formula is going to be f times f0, right? So hang on, it's v, it's v. Okay, so in other words, v is equal to lambda f0. Okay, and then I put in my formula for lambda here, so that my v is equal to v plus vs over fs f0. So the frequency observed by the observer, right, is solving for f0. So I bring this up and bring this down. I got v plus vs, and then f of the source. Okay, brightness settings. Yeah. Okay, so if the source is let's say the sound is some original frequency, right, but the source is going away. So if the source is going away, right, then I'm plusing this speed, so this divided by a larger number is small. So this is like 0 point something, it's a factor smaller than 1. So if I time something smaller than 1, my observed frequency is lower than the original frequency. So if you hear a car moving away, right, the car moving away, the frequency decreases. Okay, so that is what happens. Then what happens if the car is going towards you? Okay, so going towards you is the same calculation. So source towards observer, right? So if the source is going towards the observer, what's happening? My observer is still standing here, and then is running this way, right? And then emitting the sound with some wavelength lambda. So I will derive the formula for the wavelength is the same as before, right? So source still emits the frequency fs, okay, so frequency is still fs, right? And then speed of sound relative to the source is now what? Relative to source is now v minus vs. Do you agree? Okay, so sound once you emit the sound, right, it will naturally travel through the air at speed v, right? So if you are emitting the sound, right, so if you're emitting the sound will travel in the air at 340 meters per second, and then you're running forward at 10 meters per second. So the speed of the sound relative to you is going to be going away from you at 230, right? So you minus that is why. Okay, so you're trying to chase after the sound, that's why you minus. Okay, so you're going forward. Okay, so if you're going forward is the minus, and then so from here we got the relation that speed of sound, right? So speed of sound is equals to wavelength, and then times the frequency. So therefore the speed that we have is v minus vs. The wavelength is something I try to calculate now. The frequency is your emission frequency, so source, right? So the wavelength generated is lambda is equals to v minus vs over the frequency. Okay, so this is the formula for the wavelength generated. So now what's the speed of sound relative to the observer? Still the same, because observer is not moving. Is equals to v. So the speed in the case of the observer, right, is still wavelength and then times the frequency. So v, and then the wavelength is this thing, so v minus vs over fs, and then the frequency is, we are talking about the observer, so what is the sound that the observer hears? Okay, so the sound that the observer hears is this thing. So solving for f0, I got v minus vs fs. Okay, so as you can see, this is minus, so I'm dividing a lower number, so I hear a higher frequency, right? So this is a so observer hears a highest frequency. If the sound is coming towards you. So this one is like what you see in the cars, or you know, if you are in the audience of a F1 racing, right? This is even more obvious. So you hear the frequency of the car coming in. So when the car is coming towards you, the frequency is higher, right? And then once it passes you, it's going away from you, the frequency becomes lower. So if it's going towards you, it's higher, but it's going away from you, is lower. So in this case, observer hears a lower frequency. Okay, sorry, this room is getting dark, so let me turn on the lights. Hang on. I don't know if it makes much of a difference, but yeah. In any case, these are the results that we got. So does anyone have any question so far? Lightroom. What's Lightroom? I don't get it. So yeah, so when we talk about light, right? Yeah, this one is like not in our course, but if you're interested to like the EM radiation, the Doppler effect, right? Because light, the speed of light is constant, right? So when we calculate the Doppler effect for the speed of light, right, is the speed is constant, right? And the frequency is also constant, because when we talk about the vibration, the frequency is also constant. And what you need to change is the wavelength. So this is where we have the thing called red shift and blue shift. So this is for EM light. So it's not the speed that changes, but rather the wavelength, right? So we measure the color that we measure changes, and this is red shift and blue shift. And this is how in space we can astronomer can detect whether an object in space is going away from Earth or going towards Earth. Is you measure the blue shift or the red shift. If an object is going away from Earth, then the wavelength is longer, so you get the red shift, right? So the light coming from an object going away is actually more red than normal. But if an object is going towards the Earth, right, the object looks more blue than normal. So that is the blue and red shift. It changes the wavelength, and therefore it changes the color. Okay, so now notice that when we do a calculation, right, if my, so we assume everything is going to the right. So if my object is moving to the right, I got a plus sign. If it changes direction, I got a negative sign. So the same thing happens here, right? So if I'm moving in one direction, I got the plus sign, but if I change direction, I got the minus sign. So we need to keep this in mind, because what we're about to do is I'm going to combine both cases now. So it's going to be a bit more complicated. Not a bit more, it's just the two things mixed together at once. So it's just twice of the factors to consider. is that both are moving. Okay, so if both are moving, how do we calculate? So I got the observer that is moving and the source that is moving as well. Okay, so let's say I'm V observer is VO, V of the source is V source, right? And then the source emits the sound, and we got the wavelength. So what happens here? Okay, so what happens here is, well, we repeat the same calculation, just that now they are both moving, so we just need to take both into account. So we have a source emit sound, at frequency, the original source frequency fs. Okay, so that one is there, right? But now, right, the source is moving, so speed of sound relative to source is equals to, well, source is moving away, right? So I'm emitting the sound behind me, and then I run forward somehow, so I see the sound going away from me at a higher speed. So relative velocity, I must plus the magnitudes, right? So makes sense, right? Then what is from these two information, what is the wavelength generated? So I can get a formula for the wavelength generated is using the formula, the speed is equals to frequency times wavelength. So my wavelength formula is V plus Vs over frequency source, right? So this is when both are moving. So this is when source is moving. Then this is the expression of the wavelength depending on all this other info. Then now what does the observer measure? So firstly, speed of the sound relative to the observer is, observer is moving here, the sound is coming in, and then you're running towards the sound, so it's even higher speed, right? You see the sound coming in faster than normal, so V observer plus, okay? Then frequency observed, okay, so we are using the formula that V, the speed is equals to wavelength times the observed frequency. So this was the wavelength that I can substitute here. So V plus V0 is V plus Vs over the frequency Fs VO. So my frequency observed is just this divided by this. Okay. So this is when both are moving. So I'm drawing in such a way that both are moving into the right direction. This is the formula I got. So if this one changed direction, then this one changed a negative sign, right? If this one changed direction also, this one also changed a negative sign. Okay, so yeah, right? So so that means, right, just to be clear, right? So if source change goes the other direction, right? So that means my observer and then my source, so they're running toward each other, right, making the sound. So my VO is still the same, but my V source is going to the left. So what is the formula I should use? So I just change the direction for my V source. So my F observer is V plus VO, and then V minus V source, Fs. So this is a larger number divided by a smaller number, so definitely you will hear a higher frequency if they are coming towards each other. Okay, and then on the other hand, right, if observer goes the other direction, then yeah, so I guess you can see what's happening, right? So you just need to change the sign accordingly, right? So the observer is here, so the observer is going away, source is going this way, right? So they're moving away from each other, right? Then the formula that you need to use is I just need to change the sign of the observer. So I got V minus VO, V plus VS, frequency source, right? So here, this time you hear a lower frequency because definitely lower, they are going, both moving away from each other. And then there's a third case if both are going the other direction. So that means both are running this way. Right, so both are running to the left now. So if both are running to the left, I change the sign of both of this, right? So frequency is equals to V minus V0, V minus Vs. Okay, so it just change the sign accordingly, then you still get your solution. Okay, so yeah, so I believe this covers all the possible cases, so you should be able to calculate any situation that you come across, right? So just it's all here, so you can just refer to this. Pretty easy when it comes to Doppler effect. Yeah, so actually when I'm preparing to teach Doppler effect, I actually keep confusing myself because of my research, right? I'm actually more used to relativity, and then yeah, the concept of relativity is more natural than the normal, so-called normal Doppler effect, and I keep confusing myself over and over again. But for you guys, it's going to be in the other direction, right? So the reasoning and the argument, I believe it makes sense to you, right? Relative velocity, all this coming in. But when we learn chapter 10 relativity, these concepts need to modify. So then it will be confusing. So but hopefully everything should be so yeah, but the relativity that we learn, right, is still basic, so everything should be still okay. Does anyone have any question? Yes, essentially the Doppler effect is, yeah, a bunch of people chasing each other, right? So the sounds and things. Yeah, so have you guys seen like those submarine movies? So in submarine, right, the submarine, when the submarine want to fight each other, under the ocean, right, they can't see, so what they use is sound. So they use sound to detect each other's position, and yeah, so then this is also basically what you get, right? So that is also the application for Doppler effect. Yes, sonar, yeah. So let's say like these two are like enemy submarines, right? So so sonar, there's two types of sonar, right? If you're familiar with submarine movies, the active sonar and passive sonar. The active sonar is you emit the sound, right, and then you hear the reflection. So based on the time taken for the reflection to come back and the frequency of the reflection, you can determine the position and velocity of your object, right? So that is the active sonar. The pinging, yeah, the ping, correct. So that's the ping. But the drawback of having active sonar, right, is that because you're emitting the sonar sound, so the enemy can also hear you based on your emission, right? So sometimes you don't want to do that, so that's why you use passive sonar. Passive sonar, you just listen. You just listen to the sound and then see where the sound comes from. And I think because of this, it's harder to determine the velocity. You can try to get the direction, right? Because when you hear, you can figure out the direction, the position, but the velocity is a bit harder to determine. So it's a strategy, when do you decide to use active sonar, when to use passive sonar, that kind of thing. Yeah, so yes, that's what I was talking about. Yeah, if you send out a pinging signal, then other people will know you're there. So yeah, I used to there's a lot of like very nice submarine movies, right, that I like to watch, like The Hunt for Red October, and Crimson Tide. Yeah, the action scenes are like something like this. So let's do example 9.6.1. I have a police car siren emits a sinusoidal frequency. So frequency source is 300 hertz, right? And then the speed of sound in the air is 340 meters per second. So we just use whatever is given to us. The air is still, and then find the wavelength of the waves if the siren is at rest. So this one is not yet Doppler effect, but just calculate the wavelength. So let's just calculate the wavelength. What is it? Let me take this and adjust this. Okay. Yeah. So let us calculate this, right? So if at rest, then we just use the normal formula. So V is equals to frequency times lambda. So what we want to calculate is the wavelength, right? We know the frequency is just, so it's this divided by this. So it's 340 over 300 is 1.13 meters. Okay, so this is the wavelength. And then the next part of the question is find the wavelength in front and behind the siren if it's moving at 30 meters per second. So let's say I got a siren, right? And then this siren is moving at 30 meters per second. So this is the V source is 30, right? So it emits in both directions. So in front of the siren, right? So if I'm in front, so let's say I got observer front, and then I got the observer that is at the back. So let us calculate the front first. So the speed of the front wave hang on. So wait. Yeah, I think we can just use this formula straight away, right? So let's look at this. Okay, so what I have here is wait, what's the question asking? I forget. Oh, okay. Yeah. See, again, I keep confusing myself because of relativity. Find the wave. We just want to find the wavelength, right? Not yet the frequency. So yeah. So let's find the wavelength. Okay. So let's find the wavelength. So let's say in front, right? Speed of sound relative to source is V minus Vs, right? So you minus because you're emitting the sound in front of you, but you're going forward, so you are sort of chasing behind the sound. So the sound is traveling at a slower speed from your perspective. Okay, so from there we got the wavelength generated. Okay, so I got the speed is equals to wavelength and then times the frequency. So V minus Vs is equals to the wavelength that you want to calculate and then the frequency that is given. So we just want to find the wavelength. So the wavelength is just V minus Vs over the frequency. So the speed of sound in the air is 340. The source is moving at 30. The frequency emitted is 300. So the answer for the front is 103 meters of wavelength. Okay, so this is in the front. It's raining, suddenly raining heavily, so let me close the window. Hang on, I'll be back again, sorry. Yeah, any question? Oh yeah, Malaysian submarine. I mean, nothing much about being a man of culture lah. Is, you know, those two are very famous movies, right? And when I was much younger, right, like before university, I used to read the Tom Clancy novel. And then the Tom Clancy novel, they talk a lot about the submarine and they discuss all the details. So until now, I still remember there's like the sonar things and things. And then, yeah, and because if you're inside the ocean, right, there's a temperature gradient in the ocean, and that will affect the propagation of sound as well. Because the speed of sound, I think, also depends on temperature or something like that, I think. And then the salt content will also affect all the sonar things. So yeah, so that is example 9.6.1. Let's go to the next example. So this one is pretty straightforward because we're just carrying on from the previous example. If a listener is at rest and is moving away, the siren is moving away from the listener. So what does the listener hear, right? So it's carry forward from the previous example. That means my listener, so this is the back observer, right? So the back observer is here, and then the siren is moving away. The speed of the siren is 30 meters per second. So the wavelength is 103. So the frequency, the sound that you hear is V is equals to the F observed and the wavelength. The wavelength we have calculated already because the frequency observed, the wavelength was V minus Vs over wait, I just calculated the front case. I haven't calculated back. Sorry, I distracted myself talking about submarines. So in the back, at the back, right? So speed of sound. Yeah, so let's solve the back case first. What is the wavelength behind the siren? So what is the wavelength behind the siren? Speed of sound relative to source is V plus Vs. It's just the opposite of the other case, right? So the wavelength generated is V minus Vs is equals to lambda times the frequency. So the lambda is V minus Vs over the frequency. So it's 340 minus 30 over 300. So the wavelength was 1.23 meters. So it's longer. It's a longer wavelength, right? So this is you can also interpret this as a kind of redshift because you're moving away from the object, then the wavelength gets stretched out a little bit. Okay, so this is at the back, and then in the next example, right, example 9.6.2, we want to consider this case that the siren is moving away at 30 meters per second. So the wavelength is V is equal to F lambda, and the lambda that we use is from here, which is I know the number is 1.23, but yeah, let us keep it here to practice our math. So it's F0 V minus Vs over Fs. So the frequency, the sound that the observer will hear is V minus this. Hang on, I keep making another mistake. So this is plus, then this 1.23 plus, yeah, I'm sorry. So Fs, okay, so this is 276 Hertz. Okay. Yeah, so I blame the submarine and the rain for distracting myself. So yeah, so that's it for chapter 9, right? So these are the topics that we were covering about waves and oscillations. Yeah, so I guess you found the mistake, right? So it should be plus just now. It should be plus. Now you mentioned it, it reminds me of another thing some more. The Bojack Horseman underwater city. So I think underwater city is possible but might be too expensive because you need to pressurize everything. it's almost as difficult as building a space station, right? So yeah, because underwater is the pressure is, yeah, water pressure is very high, so you need to build a strong room, yeah, otherwise all the water will leak in and things like that. So what time are we at now? Hang on, let's check the time. Oh, okay, so my colleague replied already. For the student helper fee is RM 8 per hour, 8 ringgits per hour. Yeah. Okay, so since we finished the topic, right, and let's take a bit of an early break, because the next thing we'll start is relativity. So it's a different topic, so let us take a 10 minutes break now, and yeah, we continue 10 minutes later. Okay, so with special relativity. So I'm going to start recording here and here. Yeah, I know it's a bit hard to understand. That's why that's the main reason why I decide to rewrite and change the style a bit. So let us let us continue with chapter 10 now. So this is special relativity. Yeah, so I don't know whether this is something you guys find interesting or you dislike this topic. I think students who don't like this topic is because the concept is very strange and hard to understand, but other people might find it interesting is because it's strange and exciting, because a lot of strange implications come out of special relativity. So yeah, so hopefully you're more interested and excited rather than being scared of this topic. We just go through this slowly. It's not that difficult. Special relativity is still pretty basic. So the idea of special relativity, right, is using coordinate system. If you remember, right, back in chapter 1, we talked about relative velocity and relative motion, and that is because different objects, if you use different coordinate system, then our observations will be different, right? So that is totally makes sense. Hang on, let me full screen. Yeah, so yeah, so that is totally understandable, right? Different observer will measure different results. For example, if I'm standing here, right, and then I have a bottle that is to my right, but for another person the bottle is to the person's left, right, and so on and so forth. So it's all about like relative positions and things like that. So yeah, another simple example is we are in Malaysia, right? Where is India? India is to our west direction, correct? But if you're in England, India is to your east direction. So it's different, right? So that is because we are using different coordinate system. So that is the thing that we need to handle very carefully if we want to go through special relativity. So before we do that, right, let us do a quick review about Galilean transformation. So Galilean transformation is the stuff that we learned in chapter 1. That is before relativity, but let us reformulate Galilean transformation using the notation that we will use today in this chapter. So yeah, we talk about different coordinate systems, right? So let us like make it easy to imagine. So let us imagine two persons. In physics, people always use Alice and Bob. Okay, so Alice is a person that is using a coordinate system. I will call it a coordinate system S, right? Sometimes you see the textbook, they call it a frame because it's like a frame. The axis looks like a frame, right? So S, and then another person which we will normally call Bob, he uses coordinate system. Also, yeah, we call this frame as well, and then we call this S prime. Okay. So these two coordinate systems are moving relative to each other. So that means velocity of Bob or let's say speed. yeah, because to avoid confusing ourselves even further, right, let's think of it as the simplest way. So speed of Bob relative to Alice we are going to call this U. Okay, so I have two person, right? One person is Alice, the other person is Bob, and they are moving relative to each other at speed U. Okay, so Alice will see Bob moving away from her at the speed U. Okay, then the direction, yeah, we can figure out the direction later. Okay, so yeah, and then our second assumption we will make is at initially Alice and Bob are in the same position. And we are also considering inertial frames. Inertial frames means U is constant. So no relative acceleration. Okay, so yeah, because if one of the frame is accelerating, then we cannot have relativity anymore. In fact, we need to go to general relativity, right? But so let us discuss this type of situation, starting with Galilean transformation, and then we go to special relativity, still using the same assumptions. Okay, but remember what we were doing last time, right? So last time in chapter 1, we have two coordinate systems, right? So Alice is over here, right? So this is coordinate system S, and then Bob is over here. So this is the origin of Bob. Okay, and then this is the coordinate system S prime. So this is just S. Okay, and they are moving. Alice and Bob is moving away from each other. So as time goes on, right, this is UT. Okay, this is the distance between Alice and Bob, right? Is UT. And then if they both observe a point P, right? So what does Bob observe? According to Bob, right, this is the X position. So the coordinate observed by Bob is X prime. The coordinate observed by Alice is X, right? So this is just, remember, we are still talking about chapter 1. I'm reminding what we did in chapter 1, and then we see how to change this for relativity. So firstly, the position of P measured by Alice is equals to X, right? And then the position of P measured by Bob is X prime. Okay, and when we were doing Galilean transformation, right, we learned how to figure out the relation between X and X prime, right? So if I know this point P, right, if I know where I am and I see where is Bob, I can predict what is Bob measuring, right? And then if you can, yeah, so what is the relation between the two? So the relation between the two, you notice that X is just this length plus this length. So X is equals to X prime plus UT, right? So this is the relation between the two. So this is the Galilean transformation. Between S and S prime. So given a X prime value, I can convert this to the corresponding value of X. Or if I know X first, I can calculate what is the X prime. So this is a transformation between coordinate system. Okay, so this is the position, right? But in chapter 1, actually we deal quite often also with the velocity. So if I differentiate this with respect to time, then this is the velocity measured by Alice, and this is the velocity measured by Bob, and this is the relative velocity between the two of them. So in chapter 1, we express this as Vp Alice, and then this is Vp Bob, and then this is V Bob relative to Alice. So now you know why we call this Alice and Bob, because Alice is A, B is Bob, right? So that is the reason. Okay, so that is the Galilean transformation. Okay, so if I observe something, right, this is the velocity of the object. If Bob measures this velocity, then Alice will measure a different velocity. Okay, so let us see what happens if both of them try to measure the speed of light. Okay, so Alice and Bob tries to measure the speed of light. Am I recording? Yes. Yes. Oh yeah, I guess if you're in Malaysia, we will call Ali. Yeah, in primary school, right? The typical person is always Ali. Yeah. And how about B? What's B? What's a common name for B? I also don't know. I can't think of one. But if Alice and Bob tries to measure the speed of light, right? So let's say this, right? So if Bob measures the speed of light, okay, V prime to be 3.00 times 10 to the power 8 meters per second, then Alice should, right, we expect Alice should measure V is equals to V prime plus U. So if let's say, for example, right, let's say if U is equals to 1 times 10 to the power 8 meters per second, then the measurement of Alice is 3 times 10 to the power 8 plus 1 plus 10 to the power 8. So Alice will get 4 times 10 to the power 8 meters per second. Okay, so that is what we expect if we obey Galilean transformation. So the speed of light in one frame should be different because, you know, if we measure different relative velocity, you get different results, right? But I suppose everyone, a lot of you have already known, right? The speed of light is a constant in the universe, and and this is actually not true, right? So we can actually do the experiment. And we will find that the speed of light is, you know, is always the same. But before we could go to that, right, let me bring up another issue. Okay, this is also partially I can bring this up because you guys were talking about the light when in the context of Doppler effect, right? So let us talk about light as an electromagnetic wave. Okay, so yeah, so when we did chapter 9, right, in the past few weeks, right, so we were talking about wave as a disturbance in a medium, and then the V is equal to F over K, and also frequency times lambda is the velocity of the wave in that medium. So right now, right, I'm just like recapping the stuff that we've learned, because in relativity, you know, everything will be like modify the concept, right? So yeah, so this is what we learned in chapter 9. Okay, so so in this case, right, we can take the medium as a frame. So okay, yeah, so in this case, right, so if I have a sound, right, when we talk about Doppler effect, right, or the guitar string, I can take the medium as the frame S, then this is frame S, yeah, frame S, right? So the speed of the sound is the speed in this medium, and then can take Alice, or I'll just take Bob as frame S prime, right? And then when we talk about Doppler effect, right, so I got the sound, yeah, so when we were talking about the Doppler effect, right, so if this person is going toward at U, and then it's propagating, the light is propagating here, then the speed of sound measured by observer is equals to v plus u, right? So this is the speed of sound relative to air. Okay, so this is why I gave the speed of sound relative to air 340, right? So relative to air, and then relative to observer is, you calculated according to this formula, right? So this one, don't worry about this. I'm just like discussing this issue for us to think about, to prepare us for the special relativity. Okay, so the thing that the reason why I bring this up, right, is because when we are talking about the sound, the medium is the air. So when it comes to electromagnetic wave, is the medium for electromagnetic waves. Okay, so yeah, can you guys guess, or is it something that we can even imagine? Actually we can't, right? So this is kind of a trick question, because the answer is no, there's no medium. Okay, so let me explain why. If there is a medium, right, then we can see light everywhere. So no matter where we are on Earth or in space or anywhere, right, we can always see light. So if you believe that there exists a light, there's a medium for light, then it must be everywhere in space. So there must be this medium called the people call this the ether. Call it ether, AETHER, right? So then there must be some speed of sound, speed of light relative to this medium, and then so what we can do is, well, if light is a wave that is propagating in some medium, and then we are moving relative to this medium, then there should be some kind of changing of the speeds, like similar to the Doppler effect. So what people do is they measure the speed of light in the x direction, and then they measure the speed of light in the y direction, and they try to calculate the difference. So that is the Michelson-Morley experiment. Okay, so according to the Michelson-Morley experiment, the speed of light in any direction is always the same. Okay, so the speed of light is always the same, and then speed of light is the same. For any frame. Okay, so these are the two results of the Michelson-Morley experiment. So that is so light, right, is that is the strange thing starts to come in, because everybody understands relative velocity, right? So if I throw a ball and if I run towards the ball, I can calculate the relative speed, right? So that is pretty straightforward. If I drive a car forward at 10 meters per second, and then if I throw a ball at 5 meters per second, so the ball will come out at 15 meters per second relative to the ground, right? So everybody understands for normal object, but for light, it's not like this. Light is always same number, 3 times 10 to the power 8. That is the unique thing about the Michelson-Morley experiment, and it seems to be always true. No matter how accurate you measure, this seems to be always true. So the result is the speed of light is always this value, and we will always call this C. Usually we call this C, 2.998 times 10 to the power 8 meters per second. Yeah, so regardless of direction or any inertial frame. Okay, frame. So that is what I want to convince you. Like, this is just a long story, but if you forget the details, doesn't matter. I just want to as long as you are convinced that the speed of light is always this number. Okay, it's a very high number, but it's a finite number, so it's not infinity, right? So the light doesn't transfer instantaneously. It's a finite number, and it's good that it's a high number, because later we will see that nothing can travel faster than light, right? So it's already then it's good, it's a high number, right? So that is the constraint that we need to work with. And so because speed of light is always this, right, then what's wrong with the Galilean transformation formula? Okay, so that is the problem that we want to solve over here. Okay, so if the speed of light is always constant, but the Galilean transformation predict that you get different result everywhere. So how do we settle this problem, right? So that is not an easy problem to solve if you are encountering this for the first time. But as we now know by now, right, Einstein managed to solve this. So now we know this as Einstein's theory of special relativity. So this is what we want to discuss now. So so what I've been doing up till now is just telling story, right, to understand the problem. So now we actually address the special relativity. So this is section 10.2, postulates of special relativity and the concept of simultaneity. Okay. Yeah. How do physicists know the speed of light is fastest in the universe? We will actually prove this later. Well, probably next week. Yeah, Monday. Frame is coordinate system. I've written it here. Sometimes you say coordinate system S, or coordinate system is too long word, so I call this frame S, and then frame S prime. Okay. Yeah. So we'll actually explore why the speed of light is the fastest in the universe. But just to give a quick answer, objects with mass cannot reach the speed of light. Only objects with zero mass can travel at the speed of light. So light has no mass, so light can travel at the speed of light. Gravitational waves, graviton has no mass, so it can travel at the speed of light as well. Okay, so yeah, right. So now let us try to address this contradiction, right? So we have Galilean transformation, but our measurement of speed of light does not agree with Galilean transformation. Okay, but then so how do we handle this problem? So this is Einstein, 1905. This is the postulates of special relativity. Okay, so it's actually pretty straightforward. Postulates is something like assumptions, or is something similar to axioms for math people. It's just that some starting assumptions that are sufficiently reasonable, and from this assumption we try to derive the consequences of it. So let's start with the first postulate. It has only two postulates. So the first postulate is that the laws of physics are the same in all inertial frames. That is kind of obvious, and it's actually super obvious because we kind of been using this the whole time, right? Because what this is saying is that the laws of physics are the same for everybody, right? And we have been using Newton's law in a rolling object, tennis ball, in a spaceship, on Earth, near Earth, on a planet, right? We use the same set of laws every time. So that is a pretty obvious assumption. So there is nothing controversial about this. Okay. Then the postulate 2 is essentially the consequence of this experiment. So postulate 2 is taking this experimental result and taking this to be the postulate. So postulate 2 it says that the speed of light is the same in all inertial frames. Okay, so this was proven in the Michelson-Morley experiment. Okay, but let me quickly say for now, because this is the immediate implication. The implication, right, is that the speed of light is the same. And what is speed? Speed is displacement over time, like velocity, right? Velocity of light, speed of light, doesn't matter. That means the position and time will be different. May be different for different inertial frames. Okay, and why is this so, right? So yeah, so let us continue discussing about this, right? So the consequence is that if postulate 2 is true, these people already performed the experiment to prove that it's true, then what happens to the Galilean transformation? So the Galilean transformation, right, we started with this, right, Alice frame, Bob frame plus ut, and then what we did was we differentiate both sides with respect to time. We got this. Okay, so we have the experiments show that this cannot be true. Okay, so now we can systematically understand what went wrong. Okay, so yeah, let me write this for future reference. Where is the mistake? Okay, if this is not true, so where is the mistake? Yeah, 1905 is the miracle year. Yeah, he wrote 4 papers in 4 separate topics, fields, and then he got the Nobel Prize for Brownian motion, which is probably like the least. Is definitely important, yes, but he's not famous for Brownian motion. Let's say this. He's famous for relativity. Correct. Yes. If speed of light is constant, then distance and time is not constant. We will actually prove formulas about this later. Correct. Yes. So that is our strategy for today. Yeah. So starting with postulate 2 and 1 and 2. 1 is kind of obvious, but yeah, we push out. We start test our assumptions to the limits. Right. Let's see how far we can go. Right, and let's see the result is nonsense or correct or not, right? So that is theoretical physics, right? So you got a theory, right, and then we calculate the consequences and see how true it is, right? And of course, in theoretical physics, sometimes it's not true, sometimes it's true. When it's true, like Einstein, you get famous or the Nobel Prize. Okay, so yeah, where is the mistake in this formula? Well, the answer is the following. Well, let's see what happens when we go from here to here. We are differentiating both sides with respect to time. So we differentiated sides we are differentiating this, right, left and right with respect to time. If we do this right, that means this assumes Alice and Bob uses the same time. Okay, so now if we want to continue with special relativity, right, and if we agree, yeah, the Michelson-Morley experiment shown that this is not true, that means we have no choice but to abandon this assumption that that the 2 frames use the same time. So yeah, So we need to abandon this assumption. So the consequence is time is different, or time works differently in S and S prime. So a person's time is different from another person's time, right? So that is, and this is one of the things that maybe students cannot comprehend the brain, right? But hopefully nowadays this concept is getting more and more popular, right? So maybe it's not so strange anymore. If you watch the movie Interstellar, right, it's inside a movie already, where the time is different for different thing, you know, like the Matthew McConaughey, he's still very young, and then his daughter is like the old lady already, right? So the time is working differently. Okay, so that is so maybe if you having movies like this kind of helps to digest, right? Because it sort of tells the story in one way or a different way, right? Yeah, the water planet, then 1 hour is like 7 years. Yeah, yes, I also agree lah. In the movie, explain the concept of wormhole is like very stupid. It is, and it's not very elegant in that way. Okay, so this is where in this chapter, what time is it now? This is where in this chapter we start to discuss the concept of simultaneity. Okay. Simultaneity is like the English word simultaneous. Simultaneous means at the same time. So what we are going to explore is simultaneous events in Alice frame may not be simultaneous in the Bob frame. Okay, so if you see two things happening at once in your perspective, right, but other people look at it, it's like different order of events. So simultaneous events. So simultaneous events means this is just English, not really a mathematical definition. It just means two events happening at the same time. Okay, so right. So and to understand this, right, we will do the thing that Einstein called the thought experiment. So what we're going to do now is we will consider a thought experiment. Okay, because Einstein was German, we follow his German word. It's called the Duncan experiment. Okay, so thought experiment is like, we just imagine a situation and try to get a consequence out of it, and let's see how we go, right? We are just like following postulate 1 and 2, and because this is not true, so we abandon the concept that they both have the same time. Let's see what are the consequences that we can imagine out of this situation. Okay, so this so again, right, Alice, let's consider a situation where Alice is standing on the ground. So she's using frame S, and Bob is on a train. So S prime. So Bob is definitely moving relative to Alice. Okay, so so this is the situation that we want to consider over here. So I'm going to draw pictures, but it's going to be ugly, so let me show you a nice picture first, right? So I have Bob and Alice, and then I have a train. So I want to imagine a situation where if simultaneous events, right? So let us imagine a simultaneous event. So let us suppose that a lightning strikes at the two sides of the train at the same time. So so the consequence is the same time for Alice doesn't mean the same time for Bob, and then the same time for Bob doesn't mean the same time for Alice. We will derive this consequence now. Okay, so let me draw this situation. Okay, so yeah, then in this situation, lightning strikes at both ends of the train. Okay, so that is our setup. So now let's draw the picture. Okay, so let's say, right, initially, so remember our initial assumption is initially Alice and Bob are in the same position, so the x coordinates of both of them are the same. So let me draw this initially. Okay, so initially Bob is here and then Alice is here. Okay, so what I'm going to draw now is the Alice point of view. Okay, so what does Alice see? Okay, so if Alice see something where the lightning strikes both ends of the train at the same time according to Alice, right? According to Alice, right? And then let's say the length of the train is L, so the lightning will travel L half and L half like this, right? So this is initially. Then later what happens? So later, right, it's a bit hard to draw. So later the train has moved on. Okay, so initially Alice was standing here, so she's still standing there, she's standing on the ground. Yeah, so you are Alice, so you're looking at the train, so the train will be moving away from you already, so the train has moved. So Bob is here now. Okay, then we see what happens to the light coming out of the lightning strike. So the light will be emitted as EM radiation like this. Okay, so what is happening here, right? So one thing that is definitely we cannot deny is that the two light come to Alice at the same time, but Bob is moving. So clearly, right, obviously Bob will pass through the front lightning first, and then the back lightning will come later. That one nobody can disagree, right? This one is definitely happening. Okay, so yeah, right, so if Alice sees both lightning at the same time, right, and then both light never mind, I will explain this later. So I'll just say this, right? So she concludes that both lightnings are simultaneous. But what does Bob sees? Okay, but Bob passes through the front lightning first. The back lightning comes later. So he concludes the front lightning happened first, right? So not simultaneous. Correct. Actually, just now I was looking for YouTube for the video, but I can't find it. Yeah, there's a like animation on all this. Yeah, correct. I took the picture from Resident Evil Alice, the Mila Jovovich. simultaneous is the English word lah, so same time, happening at the same time. Right, I agree. This topic is more interesting than waves. Bob. So the Bob is Bob Dylan, the musician. I can't think of any famous Bob besides him, so I just took Bob Dylan. Okay. So the reason why, right, is this. Okay, so yeah, because of postulate 2, is that we are everything now, right? So right now the important thing is no longer position and time, but the important thing is speed of light. That is our main quantity. Because previously our fundamental quantity is position and time separately, and we take them to be absolute, correct? But right now, time is no longer absolute. Okay, position is depending on your coordinate system. That one we can figure out later. But the absolute value is now c. Okay, and the speed, right, as we know, is distance over time. Okay, and why does this imply that the time works differently? Is because, right, what does Bob see is Bob sees the lightning struck at distance L/2 away from the observer. So both observers agree with this. So this one is fixed because both lightning struck at distance L/2 away from both observers, right? So because when both are here, the initial distance of the lightning is L/2, so the distance is fixed, right? And then by postulate 2, this is fixed because we are starting with the postulate where, okay, everybody agrees with the speed of light. So the only possibility is that because one wave passed through one person first, and then the only possibility is the time for both lightnings are different. Okay, because Bob definitely will pass through the first lightning first, the front one first, but both one reach Alice at the same time. Oh yeah, Bob Ross. Yeah. SpongeBob. Okay, so you guys have a lot of Bobs. Bob Ross, Bob the Builder. Bob the Builder is the kids show, right? And SpongeBob SquarePants. Yeah. Okay. So yeah, so this is what happens if Alice see both lightning arrive at the same time, then Bob will not see at the same time. So now let's go to the other case. If Bob see both lightning at the same time, Alice will not be the same time. Okay, so the case where lightning is simultaneous for Bob. Bob Ross. Okay, so now we draw Bob's perspective. Okay. Yeah, so Bob. So let's say now we are Bob, right? So Bob here, initially Bob and Alice are in the same horizontal coordinate. But lightning initially strikes, right, like this, and then right now I'm drawing the case where Bob is the lightning is simultaneous for Bob. So if I'm Bob's perspective, right? So I'm always on the train. I'm always Bob. So Bob is here. So if this is Bob perspective, right? Where is Alice? Right? So if I'm inside the train and then the train go, so the Alice is left behind. Right? So the Alice left behind in the train. So then if it's simultaneous for Bob, that means the lightning strike comes in simultaneously for Bob, which is pretty good timing. As I say lightning, there's actually a lightning striking outside. Right? So obviously Alice will see the back lightning first, then the front lightning comes later. So in this case, Bob sees both lightning at the same time. So lightning is simultaneous for Bob. But Alice sees the back lightning first. So not simultaneous. Okay, so they cannot agree on which events are happening simultaneously. Bob Ross. Lightning. Okay, so yeah, so that is the concept of simultaneity. So how is your brain right now, everyone? Can you wrap around the concept yet? Right, so everything I'm telling, so I guess right now, right, is still pretty kind of relaxed because I'm not using a lot of math, right? I'm just telling the story, right? So I'm telling the story of the Bob, what does Bob sees and what does Alice sees, and we are just following our basic rules. So our rule is speed of light is the same for everybody, right? We are just following the rules and not violating the rules. Okay, so just follow the story and see the consequences, and it seems like the consequences is time is different for different persons. Okay, so that is the consequence of this, the postulates 1 and 2, right? Again, postulate 1, nothing much, right? It's pretty obvious. The main point is postulate 2. That is the thing that makes our concepts change to wrap, and difficult to wrap our head around. You can't understand Bob's perspective. So yeah, it's nothing much. It's just from Bob's point of view, right? If you are Bob, you're on the train, and then you see both lightning come to you at the same time. So if both lightning come to you at the same time, right? The person standing outside the train will say no. Alice will say no. Alice said, the one behind me happened first, and then in front of me happened later. So Alice, the back wave passes through Alice first. Yeah, so this is before and after. Okay, if you can't understand Bob's perspective, never mind. We just, because relativity, right? We just need one of the frames to discuss is enough, right? So that Alice is here, right? Yeah, so if the lightning is same for Bob, right? They come to Bob at the same time. In order to reach Bob at the same time, this lightning, the back lightning must pass through Alice first, and then it must cut so that both can reach Bob at the same time. So Alice will see behind her, the lightning behind her happen first, and then the front will happen. So the events are different. But if using sound wave, right? No, we can actually, yeah. If you're using sound wave, yes, yeah, definitely. Yes, Charles, she will see the near one first. Yeah, so that's the thing. But for sound wave, right? For sound wave is different. Why? Because for sound wave we can still use the same time. So if you are running towards the sound, right, you can hear the front sound first and the back sound later, but you can use the speed of sound to calculate what time was the sound emitted. Okay, and yeah, so you can calculate what time does the sound emitted. So because for speed of sound, right, you can have the speed of sound different for different observer. So Bob will observe a different speed of sound, Alice will observe a different speed of sound. Then you can calculate what time was the sound emitted, and both will get the same time. Yeah. Yes, so this is the important question here. In absolute terms, does it actually happen at the same time? It doesn't matter anymore, right? Since, you know, if nobody can agree, then it doesn't matter. Change in frequency of light. So at this point, the frequency is not relevant here lah, because we don't know we are not considering the wavelength either, right? So we can use the wavelength and times this to calculate the frequency, but divide by wavelength to get the frequency. But yeah, so I think both will measure different frequencies. I think one of them will be blue shifted and red shifted, but no, they will measure the same frequency. But that's actually a different phenomena, right? Whether the frequency is the same or not, right? It's a different phenomena, so we shouldn't confuse ourselves. Yeah, we should focus on this phenomena first. Yeah, so that is actually the main point in relativity, right? So in relativity, right, we can identify what are the important quantities and what are not. So in theoretical physics, we call this the invariant quantities. So time is no longer invariant, so it does not matter anymore. For the sound wave, well, frequency was important because we kept using this formula, right? Yeah. So I say it's a different phenomena because I did not tell you how this changed or how this changed, right? So if you just look at the frequency, I don't know how this changed. So we need to know like how to change this such that the speed of sound is the same. Okay, but and another reason why it's not relevant here is because we are just talking about when do you see the light, right? We don't care what color is the light or what frequency is the light coming in, right? It doesn't matter what frequency it is, right? We see which light came first. No matter what the frequency, one of them must come first. For sound wave, so were you talking about Doppler effect? No, yeah, that's why not the same, because if you're talking about sound wave, right, for sound wave, then both observer will measure different speed of sound. We get the same distance, so we can use the different speed of sound to calculate what time was the sound emitted, right? So we don't need frequency here. It's the distance over time. But the speed of sound for on the train is different for the speed of sound on Alice. Yeah, it's the speed of sound, not the frequency or wavelength. It's frequency times wavelength, then the speed of sound. So the speed of sound for Bob is different for Alice. Yeah. So yeah, I know. Yeah, this kind of thing needs to digest. I remember one question I'm supposed to answer. Yeah. So for light, because we haven't actually learned EM yet, so actually the frequency turns out is going to be the same. Wavelength will change, but that is electromagnetism, right? Yeah. So need to digest. Notion of light. actually also true, because we are just talking about the speed of light. So yeah, so we are not using the wave properties of light. We are just talking about the speed. We are not really discussing the wave properties. And also, even if light is a particle, which again, so that is another layer of complication, right? Sometimes in quantum mechanics, light can be a particle, sometimes light can be a wave, and things like that. But here it's like, yeah, whatever, we just want the speed, right? Whether it's a particle or a wave, it's a speed. We just want the speed. So kind of true. It's not really relevant in that sense. We're just getting the speed. Yeah. Can we solve twin paradox using special relativity? Well, we will discuss that, but in a way, yes, we can partially solve this. So yeah, we will come to that. Is it next week? Yeah, I think, yeah, we will come to that later. So the twin paradox is a trick question if you are just using special relativity to solve. So yeah, so we will explore this paradox I think next week. Yeah, by the way, our time is quite late already, right? I didn't realize. So but that should be end of the class. I should just stop the recording and continue the main lesson next week. But yeah, you can continue to ask questions. I'll just stop the recording first.